had one chance to launch it, your risk tolerance is 0. Failure is not an option. You go through tons of design reviews, as much testing as you can possibly do, and it's just very risk averse, that whole environment. And that's the way it's been for 50, 60 years. So it's just different now. You have to get used to, if I came from aerospace engineering at Orbital and SSL, and I have to get used to it every time I say, well, we need to take that through ATP. And these young people in Silicon Valley are like, what's ATP? You know, acceptance testing. Well, why do we need to do that? And when they go through like 5 series of asking me why, and I get to the point where I'm like, you're right, we don't need to test that part. We can move on. So then what this all means is we have this unprecedented access to data about our planet. I mean, that's what it's all about. So if we can do this cheaply and we can launch often and we can build constellations, all of a sudden a farmer can afford to buy imagery and look at his crops on a regular basis. Construction companies can look at progress on bridges that they're building across the world. Shipping companies, can obviously get access to their routes. Hopefully airplanes someday will do the same thing. It's kind of mind-blowing to think about what you can do when all of a sudden everyone has access to data from space. And it's real time or near real time, because we can put up 100 of these and provide data all day long, every day, all over the world. Next slide. Okay, so this is my Silicon Valley spin on it. I don't know if it's clear to everyone in the world, but seeing space go from space news to mainstream news, there's a force behind that. It's not necessarily the technology. The top and right parts of this intersection are what I've been talking about, so the access to space, the advances in technology that are incredible. The left and bottom are something that I think is the reason this is all happening right now. I think it's the reason we're all here. The left, private equity interest in space. This is like the space nerd billionaires, the people who cashed out during the dot-com industry, and they like space. Like Elon Musk wants to go to Mars, and that is very much the reason why he ended up with a launch vehicle company. And his proving that you can take your own money and privately build, vertically, in-house, a launch vehicle that works is the reason why investors, and that's this part, are coming forward and pouring their own money into it. And it's not just him. Richard Branson created a lot of press with Virgin Galactic. Paul Allen has Stratolaunch. Jeff Bezos has Blue Origin. All of the people in Silicon Valley who made their millions and billions, they want to go to space. They want their own space company. So that made it cool, and Elon Musk made it feasible. He made it so that investors are coming forward. The bottom piece of this also has to do with big data. So it's not just about space. It's not about interplanetary travel. It's not about going to the moon. It's about what Silicon Valley has been about for a while, which is massive amounts of data. So there's a real value that investors are seeing in this. So we are, I think, in the most interesting time in space since we wanted to go to the moon. Because there's the capability, the accessibility, and money, and the sexiness. They all come together at the same time. So this is just a handful of examples that you all know of, which is what we can use constellations for. And I think the main takeaway here, there are 2. One is that the cheap constellations make this data real-time and accessible, low cost, accessible commercially to everybody. And the second is, what's the second? That it has a really big impact. This image right here, so when I first came to SPIRE, we do AIS ship tracking. That sounds completely unsexy to me, but when you start thinking about how you can use that data to prevent illegal fishing and overfishing, piracy, you can help governments with search and rescue, you can help insurance companies identify who's at fault for a spill or a wreck, or and then this is a picture of the emissions that come out of ships, which no one pays any attention to, but if there's a statistic that says if the shipping industry was a country on its own, it would rank the 6th in terms of emissions. And people are kind of turning a blind eye to that, but all of a sudden, if you have real-time satellite data, you can optimize routes to save gasoline. Okay, thank you. Anyway, it has a broad range of implications in just the AIS application, but if you have imagery and other payloads on board that are looking at weather and climate and space, the possibilities are endless. Next slide. We also, like I mentioned, we started as a Kickstarter campaign for an educational platform. So if you have this access to space cheaply, you can offer it to students easily. So for $150 today, classrooms can buy access to our satellites. There's a payload on board that they can run experiments on, upload their own code. So it's important to make space very cool for kids so that they want to go be engineers. Next slide. The other important thing to realize is that there's an entire industry building up around this. And I'm a launch person, so this is focused on launch companies that are sprouting up. But there are all the integrators, the hardware and software companies, data and analytics, the ground station as a service. This is impacting a wide array of companies and services that you can offer all over the world. So there is an entire industry kind of coming up around small satellites. I had to say something about orbital debris, and that is in the press, there's been so many articles lately about just warning, all these new startups launching satellites into space are, crowding us. They're putting junk in space, and I just think we as an industry should be more responsible in terms of how we allow that to be reported. I think we should also regulate it if it's going to be. We should regulate it further if it's going to become an issue. But CubeSats, in particular, since I'm launching 3Us, represent a substantially lower risk. I mean, just because of the surface area and the orbits that we're going into, we will deorbit within a couple of years. And we're flying pretty low. So I don't mean to minimize the issue at all, but when Planet Labs and SPIRE get called out by name in all these press releases about space junk, it's easy to get defensive. So we either need to kind of respond to that responsibly as experts in the field, or regulate it further. So in summary, I think that there's a mindset shift that needs to take place, and that is that smaller and cheaper does not equal less. I think we've shown that in consumer electronics, and I think now that we have all this money pouring into space, to private space, we'll show that. Disposable does not equal unreliable. This goes back to the chart where I showed us refreshing our satellites every 2 years with the most current technology. So disposable actually works in our favor. We can always update our constellation. We can always have the most, the freshest kind of payload applications and software. And this is really happening. Like I said, there's an entire industry coming up. It's here, there's money for it, the technology is here for it, it's real. I think a lot of people like to pretend that these are still toys and only university platforms, but I just think we're past that at this point. And the envelope will continue to be pushed. Elon Musk wants to go to Mars, and he's going to keep pushing everyone to, the 4,000 satellite thing, that's not because he necessarily wants to provide internet, I don't think. I think it's because he wants a lot of experts knowing more about space and more about launching and just building up an expert base in America. So because we'll keep pushing the envelope and because Moore's Law will keep happening and we'll keep getting better and better technology for faster, cheaper, lighter, I don't know what to do with the regulatory environment, but I think it's clear that it needs to just be adaptable. I don't think we can define a small satellite today because I think it will change next year. And then lastly, just that the unprecedented access is really going to have a lot of impact. And I think you can compare it to when the iPhone came out and they opened up apps for anyone to create. We never thought we would have something like Uber. So when we all of a sudden have all this data from space that a normal person can access, we don't even know what the implications are yet. I think that's the most exciting part, is what people will do with that data. Sorry to run over.
Thank you very much, Jenny. Thank you. I can say only that good luck. And I don't understand what is adaptive regulatory environment. I hope it not does mean that we will use the radio regulation when it's useful, and we will not follow the radio regulation when it's not not useful, but okay, we may talk later. Thank you very much. Thank you. Our next speaker is a CNES expert. I leave him to make his slides. Morning, Tuesday afternoon.
Working?
It should be there. Yes, I have his short bio with me. I know him very well, but at least Mr. Jean Plat from CNES France, graduated from École Nationale d'Aviation Civile, Toulouse. Toulouse is the European headquarters for space. I learned it because also Yvonne is from Toulouse University. He's not here, but okay. My boss is also from the Toulouse University. That's why I hope the next small sat symposium after Prague will be in Toulouse, and I will make such a nasty jokes with Yvonne there like he did here in Geneva. Now this is just, he's not here, but I'm giving him a job to make the next small satellite symposium in Toulouse. It's not for you, Jean. But Jean is a satellite engineer in the field of radio communication, following several projects. And he is involved in several projects in the CPT level. He's active participants. Some to time, it's switching off. Participating in I2R meetings, really active participant in the working party. 7, the scientific services, disaster management, etc., etc. Microphone is yours.
Okay. Thank you, Attila, and good morning, everybody. So, well, I will say a few words about satellite mission from French Space Agency, and of course, a second part of my presentation, I will have some frequency management point of view. Okay, well, can you help me? Okay. Okay. How is it working? So it is a CubeSat.
Yes.
Okay.
Small CubeSat.
Oh, it's a small CubeSat. Okay. So, well, so 2 parts. Well, what is ISAT? A very small satellite from CNES, and then the vision of CNES concerning, I would say, frequency management point of view. Well, what is ISAT? Well, ISAT is it's for radio astronomy purposes, just to observe the zodiacal light. Well, it is a triple CubeSat, but it's a survey of the intensity and polarization of the light scattered by interplanetary dust cloud. So therefore, it is probably a better understanding of the Milky Way in the visible and near infrared. So actually, well, it's typically scientific purposes, and astronomer people, this is proposed by astronomer people in France. So, well, a high-sat satellite, well, it will be basically sun-synchronous orbit, 700 kilometers, almost circular. Well, because, well, not all satellites are very difficult to have circular. Well, the important thing is that it can be seen from Toulouse 25 minutes at a minimum elevation angle of 10 degrees. And you can see here, well, the S-band antenna and X-band antenna, well, basically a triple CubeSat structure. Well, we chose S and X-band. Well, I will explain later, but basically in terms of RF characteristics, for the satellite transmitter in S-band, well, between -3 and -3 dB watt, offset QPSK, convolution encoding, and we need 9 watt for a 3 dB watt output. And satellite receiver for also in the S-band, well, it's about, of course, the data rate is much lower because, and you can see, well, the data rate. And of course, well, it uses, I would say, standard modulation schemes already used in space, PCM modulation. Basically, well, the S-band, well, it's about 300 grams, and you need 10 watts for a 3 dB watt output. And you have the dimension, and you have here real pictures. I mean, this is not a drawing, this is a real pictures of the views of the TTC transponders. For X-band, well, this is for telemetry purposes, for the mission itself. So you have here the transmit power 3 dB watt, antenna gain 11 dB watt, so therefore you have take into account the losses. You have a result in IAP. And what is interesting to see is that the data rate can go up to 50 megabits. Actually,